Welcome back to Gabversity, where facts don't care about your feelings. It is always a pleasure to see everyone here. And today we are going to talk about the harmonic oscillator and how to actually, let me put my phone on block so that I'm not getting interrupted. Hello everyone, Gabversity where facts don't care about your feelings, as you remember. And we're going to use the harmonic oscillator. Hey, paint something, everyone's here. Tamara, paint something, I think that's it. It says 5, but the other people, anyway. All right, so why is it important? Well, remember how I said that quantum particles are actually part of a wave function? Hello. And the wave function, as you can see, look, that's where my sunglasses were on in the sun. The wave function you could think of as a spring, but that spring is made up of lots of other springs. So all the other springs, you pull them and they all bounce in weird ways, and together they make up one big spring which is moving in a weird way. So what we can do is break down all those springs into simpler springs so that we can approximate what's going on at different locations in the quantum wave function. All right? And there are two ways to do that. One is through the calculus method, and one is through the algebraic method. Hello, Beyond. Hey, welcome, my friend. Good to see you. All right, so let us start with looking at Hooke's law, which is in classical mechanics. So if anyone's done basic high school physics, True Faith, 6 books True Faith got. This is our record. So, Hooke's law, basic quantum mechanics, you would have done it if you have a basic spring, you pull the spring, and in classical mechanics it moves a certain way, right? So let me show you what that law is. Smuggle pubs, paint something. All right. So if anyone remembers Hooke's law, right, the basic thing was the force in a spring equals minus kx, if anyone remembers that, right? And the k was the number that was unique to a certain spring, and this can work with waves as well, right? So what we can do is we can actually say in the calculus method that this equals the mass multiplied by the second derivative with respect to time. Okay, so that means basically the acceleration of the spring moving in each direction, right? That looping again. I think we're back now. So as I was saying, remember in quantum mechanics, the average, right, of whatever the particle does equates to classical mechanics, and that's the law. So the reason this is important is so that we can look at the average particle. All right. So if you guys remember, welcome back. If you guys remember, we did this equation yesterday, but this is the harmonic equation, right? Which equals A sine omega t plus B cos omega t. And this is the standard equation for any harmonic oscillator. Hey, biohazard. All right. And as we remember, omega equals the square root of k over the mass. Okay? And omega is sort of like the rotational energy. You could sort of call it something like that. Okay? So, therefore, okay, they call it the angular frequency of oscillation. Okay, so that's sort of like, if you guys, you know, I mean, a lot of you ride bicycles or you know the engine of the car. If you imagine a spring going like this, that's the same as maybe a wheel going like this, right? And you can match a spring going like this with a wheel going like this. And that there, right, that speed of the axle doing that would be the rotational speed or the angular momentum. They're sort of equivalent in that sense, or analogous is the word. All right, so now we're going to say the potential energy, okay, the potential energy of a specific point on that spring moving. This is back still in classical mechanics. Once it decides to unfocus, there we go, equals half kx squared. And you guys probably remember that because that's potential energy here is it's the same as kinetic energy, which is half mv squared. When something's moving in a straight line, you got half mv squared. A spring is half kx squared, so they're analogous to each other. And when you graph this, it's a parabola. Okay, so it looks like this. Okay, now why is that important? It's important because, as you remember, as I was explaining before, a wave function, right, can look like this. Okay, the wave function, or the energy of the wave function, even any of them can sort of go like that, right? And that could be where the particle exists over time or over distance, right? And if you look at this, it's made up of lots of little waves. So here's one wave, okay? There's another wave, okay? Here's another wave. I don't know if you can see them. Here's another one, right? So that's a wave, there's a little wave, there's a wave, there's a wave, there's another wave, there's a wave here, okay? So it's an infinite amount of waves that all are made up by this equation, because you can see it here, right? So in other words, you can get lots of little equations which approximate each section of this wave. And that's really important, because that way you can actually simplify what's going on at a certain location. You can simplify the mathematics. So you can use half kx squared here, it can be another half kx squared here, another half kx squared here, right? And obviously as you get further away from that point, the approximation changes. Because if you use a simplified equation, that equation is just going to go upwards there. So it's going to become not correct as you get further away from x. But on x, it could be exactly matching. And so therefore, the whole v of x, right, the whole v of x, so v of x total, right, would equal hypothetically something like this, which is, you know, the v of x naught, right, which would be like, let's say this could be x naught, then this could be x1, this could be x2, right? So all different x's, so you have all of the little equations, right, plus, and then if anyone's done the Taylor series, in mathematics we write it like this, plus v dash, which is the derivative at x naught, okay, multiplied by x minus x naught, right, plus half v double dash, and it keeps going, right? That's called a Taylor series. And that is basically a representation of the infinite amount of equations that when you add them together, you get the total. So it's an infinite amount of these little equations, right? Okay, so what we do, right, is you use that, and I'm not going to show you because this is not a mathematics lecture, so I'm not going to show you how it's done, right? But basically, we can say that Vx is approximately equal to, okay, approximately equal to half V double dash, which is the second derivative of x naught multiplied by x minus x naught squared. All right. And that gives us a rough equation for the potential for the whole thing, right? Which is quite interesting. All right, so what we can do now is we can chuck in, now that we know this, we can chuck in the this equation with the Schrödinger equation and get this. And you would have noticed this already. That's the pixel size of the universe, right? Over 2 times the mass, second derivative, right, of the space part of the Schrödinger equation, which is the wave function, okay, plus half, and here it is, m omega squared x squared psi, right? And that there, if you look at, hold on, fix up you bugger, fix up, there we go, half m omega squared x squared, right? That section there, as you can see, is exactly looking like this one. We just swapped the k with omega. All right. And that equals the energy of the wave. So there you go. So now we've got that. Now let me turn the page so I can show you what we're doing next. All right, so now what we've done is this is the calculus way of calculating energy using what we've got is, my mind is boggled. Well, you know, with your mind, I could teach you maths over a couple of years and this would be nothing to you. So don't worry about not getting the maths. If you haven't done maths, even if you miss one maths lesson, it's all over. Maths, you basically got to know every single letter and what it means. But basically all we're doing is we're saying that's the size of the pixel of our universe squared over 2 times the mass, and the second derivative, which is it's a calculus way of making an approximation of a slope or acceleration of the particle at a certain location, plus half the mass by the angular velocity squared, right, the rotation, x squared, which is the distance or the location, and then that's the wave function, equals the energy of the wave function. And that's all you have to know at this point. You don't have to know how it works. If you've done maths, then that will be easy for you. Now, why is that important? Well, I'm going to show you now the algebraic method. Okay? We're going to rewrite the equation using algebraic method. And just like I said before, the reason that we do both sides is for cross-referencing reasons, right? You might only have half of the information in the calculus version and half in the algebraic version. So you can add them together, hey Linus, to actually figure out what you're missing to figure out where the particle is, right? That's why we do it. So here's the algebraic method. Algebra, one of the good things invented by the Arabs. 1 over 2 times the mass outside of rho squared, which is the momentum squared, plus mass by the angular frequency or angular angular velocity, sorry, squared. All of that multiplied by the wave function equals energy of the wave function. So this is exactly the same equation as this one, right, down here. But what we've done is we've turned it from a calculus equation into an algebraic equation, because we might have p squared, which is the momentum squared. We might not have the second derivative of the actual wave function, right? So we might have one and not the other. So now, if you guys, what we're going to do is find the Hamiltonian. And if you remember from the last lecture what the Hamiltonian is, I will go back and remind you, and I'll show you what we did. Where are we? Let me show you the Hamiltonian so you know what we're talking about. If I can find it. Where is it? There we go. Here it is. All right. Here. So the definite total energy in classical mechanics and in quantum mechanics is called the Hamiltonian. Okay, that's the Hamiltonian, which means the total energy. And if you remember, I drew it for you last time. I'll show you. If I can find it somewhere. Here we go. So if you remember, this was, let's pick someone. Let us pick Abyssmin Bwima, and we will say, actually, let's pick Abyssmin Bwima and or Sash, one or the other. You drop the rock. Here you got maximum potential energy, and here you got maximum kinetic energy, but it's always the sum of both. P plus K gives you a Hamiltonian. So, right, potential plus Hamiltonian. Alrighty. So let us come back, and now we know what the Hamiltonian is, which is the total energy, right? So we can rewrite it using this, which will be, right, it will be Hamiltonian, which is a vector because it's multi-dimensional, equals 1 over 2 by the mass multiplied by rho squared, which is the momentum squared, plus mass angular and location squared. All right. Outside of the wave function. All right. Sorry, what have I done? No, I've added something wrong there. All right, that's the Hamiltonian now. So if we want the Hamiltonian, which is the total energy of the particle at a time, it's going to be 1/2 times the mass by that. All right, which is pretty cool. Okay, and that there would be the kinetic, and that would be the potential, something like that. All right. So now, where are we here? What's the next step I can draw for you guys? All right. What we're going to do now is we're going to say the location, right, which is A plus or minus, and what I'm talking about, this location, this is inside the well. You can have minus A, you can have plus A, and X, and what we're saying is that outside of this well, the wave is just a wave, but when it falls in, it turns into a particle, and that particle is only moving left or right at this point. And the maximum to the right it can go is A, so like A miles or A feet or A meters, whatever, and here's negative A, and X is right in the middle, right? So here is the particle, and what we're going to say now is that the total energy, right, we can say is A plus or minus, by definition, 3 lines means by definition, right, is 1 over the square root of 2 by the pixel size of the universe, by the mass, by the rotation speed, okay, of the wave. And then it is minus or plus I, which is the multidimensional alternate universe number, by the momentum, plus mass by angular velocity by x. All right. So now what we're saying is this is a very, without doing all the mathematics, now if you know A, you could find out what the mass is, or if you have the mass and the momentum and the angular speed and the particle's location, then you can find what A is. So this is another little equation, and we're going to do heaps of examples, right? So you won't have to worry about memorizing these or anything like that. Okay, so now basically I'm going to rewrite this equation to show you that the Hamiltonian, which is the total energy, right, of that thing at any given location, is, right, h, which is the pixel size, that's h bar, omega, which is the rotation speed, outside of A minus A plus minus a half. Okay, which is pretty obvious, right? Because you're averaging that it's always at the center. So you're just getting the half of the total energy, right? Because it's always going backwards and forwards, backwards and forwards, backwards and forwards, right? All right. Now, let us show you how to calculate the various energies. So, as I was telling you before, right? You're going to have this. When the particle, let's say that Kev Born is now stuck in this well. Kev Born is the particle, right? And the particle can move backwards and forwards, backwards and forwards, backwards and forwards, right? Now, this would be, for example, let's just call this, let me call it the energy, let's call it phi 0, okay? And then phi 1 would be up here, right? And that's when the particle gets excited, hey, excited. And then phi 2 would be up here, right? And the more it gets excited, the more the particle moves up. And as we discussed in one of our first lectures with quantum mechanics, it doesn't transition. It just disappears and reappears up here, and then reappears up here. All right. Now, how do we find phi 0 of x? So that means the lowest state. Okay. Phi 0 of x. Okay. So we want the lowest energy state, okay? And that is going to be this. It implies that 1 over the square root of 2h bar, which is that pixel, mass of the particle, and omega the spin, right? This here, which we just saw before, that we figured that part out, outside of h bar, right, which is the pixel size, derivative with respect to x of something, which will be this, plus mass by angular momentum and x, okay, all by psi 0 equals 0. All right, so this is how we find what psi 0 is, because if we know the mass and we know the spin, that number is a constant, never changes, right? And if we know those and we know the location, then we can find psi 0. That's all we're doing. It looks harder than it is. That's all we're really doing. Okay. Now let's go to more. So now what I'm going to show you is that mathematically now I'm going to show you the calculus version of this. Right? It looks pretty hard. It looks hard, but once you do it, it's not really that hard. It just takes practice. But basically, they'll ask you a question in physics like calculate, psi 0. If you have the mass and you have this and you have this and you have this, all you have to do is put all the numbers in and then do some basic algebra and you'll find out psi 0. That's all. That's all it is. So now the calculus version of this, okay, is going to be this. You just have to know the equations pretty much, and they give them to you in the exams anyway. So it's a lot harder. When I'm teaching it, it's a lot harder than when you actually do the questions. And that's how I do it, deliberately. So you stress out now and not during the exam. So phi 0 of x, right, equals, we got mass by omega, which is the spin, over pi h bar, right, all to the 4th root, which is the square root of the square root, basically, right? And then we've got e to the minus m mass w over 2 by h bar x squared. Right, so once again, it's the same deal. You got mass, you've got the spin, you got mass, you got the spin. This never changes because that's the pixels of this universe. X is the location of the particle, and that's how you get that. Pretty easy. And so the thing is, because this, right, that equals that. So what you could do is you could actually put this into that equation and then get a whole long equation and then figure out other things, like you might not know what W is and stuff like that. So that's pretty good. That way you can actually do simultaneous equations and calculate if you don't know what W is or whatever. So that's the brilliance with it, right? So now what I'm going to do, I'm going to give you the general equation. The general equation, now that I've given you psi of 0, I'm going to give you the general one. And the general one's good because you can use it to solve any level. You can use it to solve the energy level 1, 2, 3, 4, up to infinity. You are the brilliant one. Nah, it just looks like that. All right, so I'm going to show it to you. This is psi. I'm actually learning this as I'm teaching it. Psi, but I've done mathematics, so this is easy. Once you do maths, it's easy. Psi n of x, that means n is basically any number you want, right? On the level of excited state. So if you look up here, phi 0, 1, psi 0, 1, 2, 3, up to like 1,000, whatever, right? Energy states. Okay. Equals some constant a, which we don't know, n, okay? Outside of a plus to the power of n psi 0 of x, okay, where the energy level is the number n, whatever it is, plus a half, multiplied by h bar omega. All right. So what is the point of this? Well, the point is that we now can know psi 0, right? We can figure it out from here or from here, depending on what we have. Once we find that, all we have to do is plug it into this equation, and then we can find any other psi we want. So the first thing you got to do is find the base one, and then you can find all the rest. And that's really important because quantum particles only exist at certain energy levels. It means that you know what energy level you need for the particle to exist. And that's important because when you create mobile phones, you need the particles to exist. So you have to know what energy level to inject so that the particle appears. Because if it's the wrong energy level, the particle will just disappear. Nothing will happen. Right? It's not like us where you can push someone and they move slightly. No, you got to push it and then they'll disappear and reappear in the next place. That's the crazy thing about quantum mechanics. All right, we've got a lot of examples to do later, but as I said, we're going to go through this first. Okay. So now, example. All right. So here is the example. Find the first excited state of the harmonic oscillator. So we want to find the first excited state. In other words, we want to know how much energy you need to inject to get the particle from the base level up to the next level. So to do that, we find the equation for the base level using the equation we just created. And then we use the next equation, the one that had n in it, to then jump up to the next level and figure out where it is. Pretty easy. It's actually easy conceptually. The mathematics is laborious, tedious. However, it's unbelievably ubiquitous. All right, let me now use the other side of the calligraphy pen and let's go. All right, so we know that psi 1, this is the excited state we want, right? We want the first energy level of x equals, and we just did this equation, A1, A plus psi 0. Okay. Right, that's what it equals, right? And then we know the equation for psi 0, which we have to put in, right? So that is going to equal A1 over square root of 2 by the pixel size, which is reduced h, right, or h bar, m omega, the spin, mass and the spin, right, angular momentum or velocity, okay, outside of minus h bar d. We're just copying the formula now, so it's not actually a big deal what we're doing now, right? Plus the mass by omega by x, okay, and then m omega over pi h bar all to the 4th root, which is square root, okay, and then we times that by e, so e to the minus, I just can't fit it, but that should be up there, e to the minus mass omega over 2h bar x squared. All right, so that's whole one equation. And then what we want to do is normalize it. So you guys remember, as I said, ages ago I said, if you lose your phone, you have to define where the phone is going to exist. Reading vertically makes it easier to understand. Cool, awesome. That's good news. So we want to define where it's going to exist, right? So we say if we're looking for our phone, it's going to exist only in my house. So it's going to exist at the furthest point to the other furthest point. That's what we're doing now, right? And the way to do that, if you remember, it's the integral of the modulus of the function squared, right? And just referring to the phone tilt. Ah, okay, yeah, I thought you were. Yeah, no worries, thank you. Okay, let's do this. So, normalizing, if you remember, is we do the integral from minus infinity to infinity of psi 1, and it's the modulus of that squared dx. So all we have to do now is, we know what psi 1 is. Psi 1 is this, and then we expanded it to this. So all we have to do is integrate this. Right? That's all we have to do. And we have a table for that. If you remember, this was the table we made a few lectures ago that we made together. That's the integral table. Right? And you don't have to worry about that if you haven't done maths before. But basically, we just have to use a table. And so what happens, once we do all of that mathematics, it turns out that in this case, just by coincidence, right, it implies that A1 equals 1. So that means, right, that means for the first excited state, we just have to put a 1 in here, and then we have the equation. And that means that we can find out exactly where the particle can exist, because it can only have one energy level. So the particle can only exist in certain places. Okay, cool. So now what we're going to do is we're up to page 48. And we're going to show you the algebraic form. Instead of having to do all of this, there's an algebraic form. The algebraic form works like this. A plus multiplied by psi of n. And remember, I showed you the whirl, right? In the whirl, that's A plus and that's A minus. So it's just the distance. That's a distance, right? So the distance by psi n, which is whatever the energy level is, equals the square root of n plus 1, right, multiplied by psi n plus 1. Okay. Now, why is that important? That's important because this is an iterative function. In other words, if you know psi of 0, right? So remember, we saw psi of 0 before, and I'm going to show you how this is done. Right? Where is psi 0? Psi 0 is here. This part here is psi 0. Right? So if you put that equation into here, and then if that's psi 0 and that's A, right, you put 0 in here and you put 0 here, that'll give you psi 1. So psi 1 will be psi 0 by A. Okay? And then you divide that by this thing to get psi 1. That's just the algebraic version of doing it. And another form, the exact same thing, I'm just going to rewrite the exact same thing. And it's going to look like this. It's going to be psi n, which means psi any level, this is now the general equation, equals 1 over root n factorial, right? And I'll explain this in a second. A plus to the power of n psi 0. All right, this is easy. I'll show you what factorial is, just to give you an idea. So 2 factorial equals 2 times 1. 3 factorial equals 3 times 2 times 1. 4 factorial equals 4 times 3 times 2 times 1. Right, and it keeps going. So n factorial is going to equal n times n minus 1 times n minus 2 all the way 2 times 1. Right? That's all that is. Okay. Pretty straightforward. Pretty straightforward. All right. So now here's another one. Find, this is an example. Find the expectation value. Now, what would you expect the value to be on the average, right? Right. Find the expectation value of, okay, of the potential energy, which we will call EP, potential energy, in the nth state. Nth state just means we're finding the general equation. So the first state, the second state, the third, whichever, right? Whichever n we want. Okay? Of the harmonic oscillator. Okay, so this is how we do it. We say that the average, right, which is here the expectation value, right, of the potential, which is, that's why we put these arrows, because it's expectation value, right, equals the expectation value of half, right, we've done this equation before, half m omega squared x squared, right, and it's the expectation value, right, and that is simply what we do with the normalizing. If you remember, it's half m omega squared. Ball handwriting, thank you very much, very appreciated. It's, I owe it all to the pen and a lot of practice. All right, the integral from minus infinity to infinity, okay, of the conjugate, which is the mirror image in the alternate dimension of the energy level state. Why is it doing that? Fix up, come on. Refocus, my friend. You can do it. There we go. All right, that's the conjugate, x squared, and then the energy state, n dx. Alrighty. So, how do we make this easy? Well, what we do is we remember that x, just that we did before, x equals stupid unfocusing garbage. Sorry about that, guys, honestly. I don't know how I'm supposed to fix that. Hold on a sec. Let me get the magnifying glass. That's like glasses for Periscope. Hold on a sec. I'll be back. All right. Coming back. Here we go. Oh, well, look at that. All I had to do was put glasses on Periscope. I'm using monocles. All right, so x, as we got h bar over 2 mass by the rotation. You're going to start seeing the same equations over and over again after a while. Outside of a plus a minus. You can see, yay! Okay? So that's x, and we know that momentum, it's just mass by velocity, which also happens to be here I, which is the magic multi-dimensional number, square root of -1. And then we've got here h bar, which is the pixel mass omega over 2, and we're going to square root that. Outside of a plus minus a minus. There you go. All right, so that's x and p. Now, why is that important? Because we take this equation, right, and we can chuck it into the original, which was here, so that we can actually mathematically integrate this easily. So let's do it. And so the expectation value of v, okay, is going to equal h bar omega, which is the rotation speed, over 4. And you can see that because when you times these two together, you're going to get, anyway, sorry, I just joined, but is h bar Planck's constant? Yes, well done, my friend. It is called the reduced Planck's constant. So it's the Planck's constant divided by 2 pi. But yes, it's based on the same number, which is the smallest possible pixel in our universe. All right. Multiplied by the integral of, we've got the conjugate, which is the mirror image in the alternate dimension, as I've mentioned before, star, right there, n, and now we're just swapping x for what x is, right, which is right here, sorry, x squared, sorry. Based upon what we said x was, we're now going to show you x squared, right, so x squared, right, is a plus squared plus, it's just expanding this bracket, right? Plus A plus A minus plus A minus A plus, okay, plus A minus all squared. And then we multiply that by psi n dx. All right, so that's the exact equation from here. That's just this. Right? All we did was put it like that, right, to make it way easier to integrate, because now we can integrate by parts. Right? That's all it is. That's just to make the mathematics easier. All right, so now, without doing all of the complex maths, I'm now going to show you that V, which is the expectation of the potential energy, is going to equal half h bar omega, right? Reduce Planck's constant and the angular velocity, angular speed, right? N plus 1 over 2. And there you go. So now the expectation of V is simply this. Solved. Cool as that, huh? All right. Now we're going to go to the analytic method. 51, 52. I'm just going to save you doing all of the work. Let me just find you the work. All right, so here I'm going to show you all possible energies, right? For example, here's one particular energy, right? If you pump the Schrödinger equation in and you get that the energy is 0.49 h omega, you get this. So this is the possible energies, right, over time, and it shows you. And that's another one. It looks like a bum sitting on a seat. This looks like a person's face looking from the top. That's their eyes and that's their nose, and they're looking this way. All right, and this is called the recursion formula. If you haven't done maths, I'm not going to teach you this, right? That's just the recursion formula. So it's part of an infinite series, which is quite amazing. It's amazing that mathematics actually can accurately describe all of this. I just love it. Okay, so now I'm going to show you the final equation. Okay, and it works like this. This is the other version of finding out the answers, and we need to know all the different ways, right? And the reason is because when you go to let's say you have to go visit your family, you need to know different ways of getting there, because if you didn't, and one of them had blocked traffic, you wouldn't be able to go around the traffic using other routes. So that's why you got to know all the different ways of solving the problems. That's really about it, really. Okay, so let me show you. Psi n, okay, of x equals, and this is familiar, m, the mass by the rotation speed or angular speed, over pi h bar square root, which is that. Okay, so we've done that one before. Multiplied by 1 over the square root of 2 to the n factorial. Okay, and we showed you what factorials was. I'll just remind you, that's your factorials. 2 factorial, 2 by 1. 3 factorial, 3, 2, 1. 4 factorial, 4 by 3 by 2 by 1. N factorial, n by n minus 1 by n minus 2, blah, 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 all the way to. Okay. So, and then we apply it by the Hamiltonian, which is the total energy, if you remember. Okay. By, here we have the energy, okay, which is in epsilon. e to the minus epsilon over 2. And there it is. So now we can know it at any level. Right? And look at this. You can see it right here. Here's a little table. The first two Hermite polynomials, right? So 1, 2, that, 8 epsilon cubed minus 12 epsilon, then 16 epsilon 4, and then 5. So it's pretty amazing. Alrighty. I think we're probably going to stop soon. Yeah, we'll stop soon. And that'll end this. And as you can see, here are the excited states, right? For different particles. Look at this one. As you excite them, that's where it can exist. It can only exist here, right? This one can only exist like this. Okay? So that just goes to show you. And here, what we see is what do we got as B? The graph of psi 100 squared with the classical distribution dash curve superimposed. Very interesting stuff. So there you go. All right. I'm going to leave that there for you. And fingers crossed, it actually made even 1% of sense to people out there. And I shall be back later to do some problems and solve them for you. And remember that you have been at Gabversity, where facts don't care about your feelings. All the best.